Hi, this is Tzvi Rosen, here with another lecture on algebra and geometry. In this lecture, we're going to talk about the projective plane. And the reason we're talking about the projective plane is because in the next 2 to 3 lectures, we're going to be building up to Bezout's theorem. And to explain what Bezout's theorem is, we're going to talk about the intersections of curves. So let's say we have 2 lines. In general, these are going to intersect in one point. Okay. How about a line and an ellipse? Okay, so here's, I actually can draw a real ellipse with this thing. Here's an ellipse and a line I can also draw. Okay, and here we find 2 points. Okay, how about 2 ellipses? Well, let's say they're in general position relative to each other. So we've got an ellipse here, ellipse here. So here we find 4 points. Okay, but just by looking at these pictures, you can easily convince yourself that these aren't the only cases, right? We've got, for instance, the case where our 2 lines are parallel. In that case, we have 0 points. Okay, you might also have your ellipse and your line being non-intersecting. So this line does not intersect the ellipse. Similarly, you could have 2 ellipses that are non-intersecting. Okay, here's one ellipse and another ellipse, and never the twain shall meet. So how do we deal with this? It seems like there's some kind of optimal situation where we have 1 point, 2 points, and 4 points, but then this 0 point situation, which applies really to all of these, could also easily happen. And you could have anywhere in between. You could have the line being tangent to the ellipse. You could have the 2 ellipses being tangent to each other, or maybe intersecting in 3 points. So the picture is really unclear. But at least in this optimal case, we would want to say, let's put this in green. We would want to say that if the curve is of degree d, meeting a curve of degree e, there should be d times e points. Okay? Because that's what we saw in these examples, at least in the optimal case. You have 2 lines, those are degree 1 curves, because they're defined by polynomials of degree 1, and they meet in 1 point. When you have a degree 1 line meeting a degree 2 ellipse, that has 2 points, and 2 degree 2 ellipses meet in 4 points. So it seems like the degrees should multiply by each other to give you the number of intersection points. And indeed, if we make the right assumptions and we count the right way, and we'll see what that means in a later lecture, then a curve of degree d will always intersect a curve of degree e in dE points. Okay? But in order for that to happen, we will need projective geometry and complex coordinates and intersection multiplicity. Okay? So we're going to talk about the projective geometry bit today. And the key there is that in projective geometry, even when 2 lines seem to be parallel, they will actually really meet off at infinity. Okay, this is the key to the key of the projective plane. So any two lines, or even so two parallel lines meet in a point at infinity. Okay. So we're going to take some time just to explore the visual consequences of this idea that two parallel lines meet in a point at infinity, and how it affected drawing in art through history. And then we're going to establish a more rigorous mathematical structure for these ideas. Okay. So let's talk about drawing with and without perspective. And the idea here is, do parallel lines meet or do they not meet? So you are going to be very kind in forgiving my poor drawing. But let's say we want to draw a road. So let's say we have parallel lines. And here's our road, and we've got maybe some trees along the road. So I'm going to draw the tree trunks first. Then some leaves. Okay, so this looks like a very basic drawing cartoon that you might see in a kindergarten class with a not particularly talented kindergartner. But the picture changes when we say, you know what, these parallel lines, the edges of the road, are actually going to meet when we go off into infinity, or into the horizon. Okay. Okay, and we're also going to have a kind of hinted line coming out along the tops of the trees. Okay, but these are also, the lines along the tops of the trees are going to meet at infinity, so we want the sizes of the trees to reflect that. Okay. So let's get the tree trunks of the appropriate size. Okay. And now we can do the tree branches, or the leaves. Okay. And you can see that even though I didn't get any more talented as an artist, the picture on the right looks a lot more realistic. Okay, it looks a lot less like a conceptual cartoon and a lot more like somebody's actual view of the real world. Okay, and here are two examples of paintings, one with perspective and one without perspective, from history. So if you zoom in to the cartoon here, I'll see if I can zoom in effectively, the image here, you'll see that along the floor, the tiles are all perfectly square. So these lines are actually parallel. Drawing a line here. Okay, so the lines defining the tiles along the floor are parallel, indicating that this picture is not projective, right? It's not drawn with perspective. Okay. On the other hand, if you look at this picture, which is the School of Athens by Raphael, if you draw lines along the tiles in the floor, they all meet at a point in the distance, telling us that this is drawn in perspective. Okay. And the painting looks a lot better as a result of that. Okay. Let's continue and try to do some more drawings of our own. So we're going to take the idea of one-point perspective and use that to draw a tiled floor. Okay, we had a tiled floor in this picture, and this is something that's done by Stillwell in Chapter 5 of his book, which I assigned his reading, where he is able to draw a tiled floor which is consistent with perspective. Okay, so the first thing you do is draw two parallel lines. Okay. And then you want to draw evenly spaced points along this line. Okay, and in order to do that, we'll use some circles. And we'll put them in light gray. Okay, so we have this. And I will paste a few copies. Yeah, let's do it this way. Okay, this is essentially a compass construction for equal points along this line. Okay. And now we can start. Let's mark out all of our evenly spaced points. Okay. And now we will take the point at infinity. So this is considered the one point that we have perspective from. And we are going to draw lines to all of our equally spaced points. Oops. Here we go. Well, let's undo that. We really want them to meet at the same point. Okay, so now we have a bunch of equally spaced points on the line close to us, and they meet in the far distance the line in infinity. So the implication at the point at infinity, the implication being these are all parallel lines which meet at the horizon. Okay, well then how do we get the next row of tiles? Well, we'll take the first somewhat arbitrarily. Okay, this just needs to be parallel to the one that we've already done. And then from there, we're going to use the diagonals to establish, oops, make this light gray. To establish where this should intersect. So you see it's the diagonal of that square. Okay, and the same goes for these. You know what, I'm gonna just take one of these guys. Okay, this should be here. And we just need this one over here. I think we've covered everything. Okay. So now we take wherever those diagonals met the parallel lines, and we draw a new horizontal line there. So for instance, we'll put one here, we'll put one here, and okay, this is going to be another one. This is another one. This is another one. And another one. And if we wanted to keep going, we could take another diagonal from one of these tiles and stretch it across. And now pulling these across like this. Okay. Here we go. It's a little bit difficult to do with this tool, but I think we're getting the general point across. You'll notice that these are getting closer and closer together as we get closer and closer to the horizon, which makes sense. Things that are further away look smaller. Okay. All right. This is probably about the limit of my artistic skill. Okay. Cool. So is this the only way to do perspective? Well, no. We could also do two-point perspective. And the idea here is, instead of just only looking at sets of parallel lines that meet at one fixed point in the distance, we allow other points we allow another set of parallel lines to meet at a different point in the distance. Okay. So let's draw our horizon. Okay, and now we're going to have, let's make these blue lines and red lines. So we're going to draw, let's skip different, like this. And a similar construction can also be found in the Stillwell chapter. Okay, and then we'll have another red pair of lines like this. Okay. Can consider this to be our main tile out here in front. And if we want to tile the floor, now that we have a pair of parallel lines established towards both of those 2 points, now we can set this diagonal to go like this. And then you can use lines from that new point on the horizon to figure out where the next tiles should be laid. And this isn't too light of a point, too light of a color. I need a little darker so I can see it when I'm drawing. Here we go. Okay, and great, now we can draw another line from here to here, and another line from here to here. Okay, and then you can carry on that way. And if you wanted to build, for instance, just a rectangular room whose tiles made it appear to be in perspective, you could do the following. Well, first let's copy that. Let's shrink this down a bit. Okay, and then we can erase any extraneous parts. Okay, and here you have a lovely rectangular tile that clearly seems to be in perspective, even though we're now missing the points on the horizon. Cool. And you can actually use this for 3D drawing in a pretty cool way. So let's say we're doing 1-point perspective. We start by drawing a horizon line and a square. Okay, let's put that here. And then you pick a point on the horizon. And this will be the point where the sides of the cube that are facing you, where they eventually meet. Okay, and then you've got this, 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 and this edge. Okay, these are all and you can pick a corner of your cube, and then you draw a vertical line from there, and a horizontal line from there, and you complete the picture. And after doing some erasing, we have a lovely cube in perspective from 1 point. Okay, that's an example of a cube in perspective. You could do a similar thing with a different type of perspective. You know, let's say the point was far. Let's say the point on the horizon was far away from where your square is. Okay, so we'll get something like this. Let's do that here. Okay, now again, we'll send all of these lines out. Okay, and then we can pick our corner. Okay, and vertical, horizontal, vertical, horizontal. Okay, and again, we've got some erasing to do. Okay, I think that's a pretty good job. And so here we have another cube drawn in perspective from a single point. Okay, and let's get rid of this. We could also draw a 3D cube using 2D perspective. So we're going to draw our horizon line. And for this, we want to take special note of the edge that's pointing towards us. That's really what's the key part of these 2-point perspective cubes. So we'll draw a vertical line here. And let's do another cube as well. We'll do 2 of them at once. So we'll draw a line here. Okay. And we're going to draw one side of the cube to this vanishing point, and the other side of the cube to this vanishing point. Okay, and then we can draw the vertical parts of the cube like this, and then we're going to connect the other vanishing point here and this vanishing point here. Okay, and we'll also connect this point to this back corner and this point to this back corner. And that should give us our whole cube. And we'll just trace it out in black so you can see where the cube is. So we've got this edge and this edge. Okay, and then we can do some, got this as well, here and here. Okay, we've got some dotted lines here. Okay, so this is the cube. We can shade it a bit if we like. Okay, that's a cube. Now we can do the same thing with the other one. So we'll connect here to here. And we can add in a couple of vertical lines for the remaining edges and do some more connecting. Okay, and now we can trace it much like the other one. Okay. Okay. And if we want, let's see if this works, we can get rid of everything here and see the resulting cubes. They look pretty good. One of them you're looking kind of straight on, the other one you're looking at down from an angle. Let's get those lines back. Okay. Cool. Let's go forward. Now we'll talk about actual math. So we have three approaches to define a projective plane. The first is through axioms, so rules about points and lines that will establish some of the basic properties of projective plane. Then we'll take a more geometric approach using lines in Euclidean space. And finally, we'll translate those lines into homogeneous coordinates. Okay, so here are the axioms. We have 2 points. For any so we have things called points and things called lines. And 2 points define a unique line, meaning that they are contained in some unique line. 2 lines define a unique point by their intersection. And there are 4 points not all in the same line. This should be in, a greater than sign. That just means that the dimension should be bigger than 1. Right? If you have all of your points in the same line, we're just describing a line, a projective line, which is not a projective plane. Okay, yeah, so any 2 points defines a line. That's something that's familiar to us, whereas 2 lines define a unique point. We know that when lines used to be parallel in standard Euclidean geometry, they don't define a unique point. But to axiomatize projective plane, we say they do in fact define a unique point where they intersect. Okay, and using these axioms, you can actually come up with all sorts of geometries that are not kind of what we think of when we think of projective geometry, like the drawings we were just doing. And here's kind of the classical example of this. So this is called the Fano projective plane, and it has it has 7 points and 7 lines, and it satisfies all of these axioms. So for example, if I take this point and this point, the line it defines is this circle that contains both of them. If I want this point and this point, then that defines this line. Okay, I'll mark this in blue. Okay. As for any pair of lines, well, all of the normal lines intersect as normal. But let's say I want to know where, this line intersects the circle. I just look for the unique point that's on both the circle and that line, and that's going to be this. This satisfies all the axioms of projective planes, but doesn't reflect the geometry of perspective, the way that we were describing so far in this lecture. Okay, so in order to define that, we mentioned lines in R3. So we're going to describe a construction. We're going to take we're going to take 3-dimensional space. We're going to put a sphere at the origin, and we're going to let that sphere sit on a plane at z equals -1. And what should we use here? Let's use gray. Here we go. So this will be sitting here at z equals -1. Okay, so this the sphere, we can say it has radius 1, and it hits it at the point 0, 0, -1. So how are we going to use this to define the real projective plane? Well, we're going to take the set of lines through the origin, and then we're going to keep track of where that intersects this plane. Okay, so here's a line through the origin, and it's going to hit that gray plane in a specific point. Similarly, this line will also hit at a specific point. Okay, so in this way we're getting lines through the origin corresponding to points on the projective plane. Okay, what if I have a point somewhere on the projective plane? How do I get that to correspond to a line through the origin? Well, you just take that point and take the unique line that it forms with the origin, and that will describe how to get back from points on that plane to lines through the origin. This almost always makes sense, but there are some lines that are parallel to the plane that will never touch it. Okay? So for those lines, okay, these are parallel to the plane z equals -1. So these will correspond to points at infinity. Okay? So we're going to kind of have this circle, this equator circle, where all of the lines through that equator, through the origin and through that equator, are going to never hit the plane z equals -1. So the projective plane ends up looking like all of the points in the plane z equals -1 plus an equator's worth of points at infinity. Okay? And actually, we need to be a bit careful because you'll note that the line that goes through this point and this point is actually the same line. So it's not quite an equator's worth, it's actually half an equator's worth. Okay? Now we can talk about what lines in RP2 in the real projective plane should translate to in terms of what that means in that sphere where we're projecting from. So again, we'll draw the sphere. Okay, and we've got our plane. Okay, so if we have a line going through this plane, that's going to translate into a circle in this sphere. Okay, so perhaps it's not so obvious why that is, but hopefully this picture makes it a bit clearer. And as your line goes off to infinity, you eventually hit the point in that great circle where it crosses the equator, and let's make it over here, and the line remains parallel to the plane z equals -1, so this stands in for that. If we choose a line, if we draw a line that intersects this one, well, then the corresponding circles are also going to intersect. Okay, and let's say they intersect this red point here. Okay, so maybe I'll redraw that circle. So let's say this is the intersection point. Okay, then the corresponding circle is going to also pass through that intersection point. Okay. And if we want to look at a line parallel to that one, so let's say we have this line, which is parallel, we're going to have a circle which meets the green circle at its points at infinity. Okay. So really, these are all just different great circles on that sphere. And the question of whether they're parallel or intersecting is just whether the point of intersection lies in that lower hemisphere or if it's on the equator somewhere. Okay. So that is all a little fuzzy because we're just kind of visualizing the lines, but let's try and attach some numbers to it. So any line through the origin, or let's call it O, is defined by a point P, and that's given by coordinates x, y, z, not equal to 0. Obviously this definition is not unique, so if you have P and 2P, which is just 2x, 2y, 2z, these define the same line. So we're going to make up a new nomenclature called homogeneous coordinates, okay, which will work like this. Instead of having parentheses and commas, we're going to have brackets and colons. And then it will be understood that represented by this triple is really any scalar multiple of it. So this squiggle means that they're equivalent, that xyz is equivalent to lambda x colon lambda y colon lambda z, where lambda is any real number except 0. Okay, and xy, and the point xyz is not the point 0. So all x equals 0, y equals 0, and z equals 0. So at least one of them has to be distinct from 0. Okay, and then with these conditions, namely by ruling out the point 0 and declaring that any scalar multiple of a point is equal to the original non-zero scalar multiple, that gives us homogeneous coordinates on the real projective plane. Okay. And an interesting side effect of this is that we can talk about homogeneous polynomials in the real projective plane. So these are polynomials where every term has degree d for some fixed d. Okay? So if that's the case, so let's say that's true of some polynomial p, then p of x, y, z, well, if we plug in lambda x, lambda y, lambda z here instead, then that's going to be equal to lambda to the d times the value of p of x, y, z. Okay? So that's not, in general, equal to the original value, but if this is 0, if p of x, y, z is 0, then so is p of delta x, sorry, lambda x, lambda y, lambda z. Okay, which means that the sets of points defined by the vanishing of certain polynomials, homogeneous polynomials, is well defined in real projective space, even though we have different triples of numbers standing in for the same point. Okay, now let's consider what projective lines look like in homogeneous coordinates, right? We saw what they look like when we're projecting from a sphere. Well, do they look like in homogeneous coordinates? Well, is given by 2 points not on the same line through the origin. Or in particular, it's given by a projective line is designated by a plane through the origin. So that, if you remember from one of your calculus semesters, I don't remember which one, those are described by equations of this form: ax plus by plus cz equals 0. This designates every plane through the origin, and so the same can be used to establish to define a projective line. Okay, so this is enough to define a projective line. Okay, let's say we have 2 points, and we want 2 projective points, and we want to know what's the projective line containing them. So for example, 1, 2, 3, and 1, 0, minus 1. Okay, these are 2 projective points. You can see right away that they're not on the same projective line. Sorry, they're not on the same line through the origin, so they do span a plane. Okay, they do span a plane. So in order to find the equation for the corresponding projective line, we just need to find an equation that vanishes on both of them. So one way to do that is to find a cross product of vectors. Another way is to solve a system of equations. Let's do it that way. X plus, sorry, so we're looking for the numbers a, b, and c. So we have a plus 2b plus cz equals 0. Sorry, plus 3c equals 0, and a minus c equals 0. So we can combine these to get c is equal to a. So we have 4a plus 2b equals 0, which means that b equals 2a. So now we know that a, b, and c are related by b is 2a and c is equal to a. So these are a scalar multiple of 1, 2, 1. But we know that all scalar multiples are equivalent, so that's our solution, 1, 2, 1. And so the equation defining our projective line is x plus 2y plus z equals 0. And you can see that both of these points do in fact lie on that line. And really we're just doing 3D geometry with everything passing through the origin. That's it in terms of the projective plane for now. We're going to use these projective planes to obtain a version of Bezout's theorem where every pair of curves has the right number of intersections, just like, as we've seen, every pair of projective lines has exactly the right number of intersection points, namely 1. You don't get any pairs of parallel lines here. Okay, thanks for your attention.